You start? Okay. Now, okay, so we're back, and this is the part about selective corrosion and selective leaching and de-alloying. So essentially what it is the removal of one element in favor of the other one being protected. So it's kind of like selective. And as we saw from the previous slides, that can happen actually at the microscopic level, at the microstructure level. So certain phases can actually, and this is what causes the intergranular attack. But the most prominent threat of selective leaching and de-alloying actually is in the boiler tubes, where you can get designification left behind a porous copper-rich plug that with little mechanical strength, and this is where leaks happen. So actually, I think here it just shows you some of the the concerns that we had and that we experienced in with some boilers. And I think the boilers, it's nickel and nickel copper.
Nickel copper. Yeah.
And the copper was actually, the rate was going a little bit more, so you actually are left with a sponge-like material. It's not really sponge-like, but it's getting there, and that's why we're doing all the inspections and to make sure that this mechanism, we don't leave it until you say, okay, your boiler now is just leaking. You can't change the the tubes. You cannot retube the boiler. It'd be easier to throw it away. And, so this is also another case Andrew was talking about. Would you like to share with us?
In our Pickering shutdown cooling pumps mechanical seals, we have in the seal a ring that's made of tungsten carbide with a cobalt binder, tungsten carbide. So we have to replace these seals every outage, which is excessive. These pumps only run a few hours, or very limited hours during operation. They run a bit during outage, but because of selective leaching, removing the cobalt from the rings, we get seal leaks developing all the time. So that's an example of selective leaching that's a problem that we're dealing with, which we haven't been able to solve other than replacing parts periodically.
So it doesn't have to be pressure boundary. It doesn't have to be the boiler, the tubes in the boiler, or heat exchangers or plugs. It can actually be like some of the applications that support the operation, the sealing. I mean, that's the so.
Yeah. So other example is in Unit 4 at Pickering, de-alloying, like same kind of a thing we have seen, and we plugged a lot of tubes, the heater area, right? So this dezinkification is a common, and it is mentioned that we concluded because of the organic anions it is causing because of the high morpholine which we added.
Yes.
Now we have reduced the morpholine, which disintegrate and decompose to the organic anions, yes. Oxalate, acetate, those things.
Okay.
So that's a good example which you have seen at Pickering Unit 4 and Unit 1 also.
Yeah, so this is one of the conditions that's happening, and of course, actually, it's part of the mechanism for that is galvanic corrosion, or actually a micro galvanic cell that is actually happening. So it's either with the global microstructure, or locally, that's actually it's causing some components to actually, or elements to actually disappear. So it's a micro galvanic cells don't have to be. It can have micro galvanic cells. So that happens actually. So okay. So here. So selective leach causes. Also, I have a galvanic cell. So it's difference in electrochemical potentials in the same electrolyte. So and prevention, of course. Well, select metal alloys are more resistant than controlling the environment. Sometimes you cannot control the environment more than you're controlling it. So it's really the the selection of the material, and that's what Andrew was saying, is that the vendor came to them and suggested, they use more resistant. Yes?
Do we also, like in CCD, monitor for some of these metals? Like, for example, for
Chemistry folks.
or something? Is that something that, like, we monitor for just
Not necessarily. Like, only some of the, like sodium, some of metal we monitor. But like, this major copper we do monitor, iron we do monitor. But for those zinc or very minor metal, we seldom we don't. And plus, through that, we not found that there's any issue that because they're too tiny, from the water you probably barely can detect it. Because water box so huge flow and they're most of the time under the detection limit for the zinc or something.
Thanks. Velocity-related corrosion. So, of course, this is FEC. And velocity-related corrosion is actually we suffer from an OPG. We experience rather the flow accelerated corrosion. Now, fortunately, we do not have, knock on wood, we never had a major problem like they had at Mihama in Japan. But that was really, when you look at the root cause of what happened, they never maintained that pipe. They never even inspected it. That pipe that actually ruptured. So we are we're focused a lot on the preventative maintenance, taking measurements, taking measurements of the system, and actually proactive replacement. So sometimes your certain areas you go, you measure with a probe, and then after 2-3 measurements, you're able to project your thinning rate or your wall loss rate, and you're able to project it further. And you're saying, well, how can I change it? Perhaps now, or maybe can I leave it for another outage or two, things like that. So this is something we should be proud of. We're doing that here at OPG. We're engaging. It's not just taking measurements and doing calculations. As a work management and maintenance activity that's actually supporting the FAC program. But really, essentially, what it is, it's increased rate due to fluid flow. It can be flow accelerated corrosion, erosion corrosion, and cavitation corrosion. So I just want to deviate here for a second. I want to show you an example of that here. Okay, I'll take it here. Okay, so this is a pipe. This is a copper pipe. So this is erosion corrosion. This is a copper pipe in air controlled, not inside the plant, but it's outside for a building. And because of the fast flow, what's happening is that, that's a unit 4.1, but you can see the flow is going in this direction here because there's a certain inclusion in the structure of the copper. So it's actually going like this. It's called claw pit corrosion. So it's actually, you can see here it is corroding right in the middle. I shouldn't actually be pointing on that. I should be using the laser. So it's actually it's here. These are pits. These are pits, and the flow is going in this direction here. And as it hits a certain part in the metal that's more difficult to corrode, to actually erode, it's going around it. So as you can see here, it's the horseshoe pitting. And right in the middle here, of course, you have, this is by you can have other pictures actually further. And here, that's a close-up. You can see actually here, the flow is going in this direction here, and this location here is more hard for the erosion, so it's actually going around it. But still, we have the pit here. Now, I'll just show you how and why. I think this section here. So this is how much lost by erosion corrosion. And what happened is actually, it's the root cause behind this. It's very important. What happened is, and I've seen this happen a couple of times, that the same approach, like the same approach, not in this particular problem, the same approach. So you sit with the engineers, sit with the system engineers, and then you determine, oh yes, okay, we know what happened wrong. So generally, you design for the water piping for the air handling units. You're assuming it is you use the equation of continuity to determine your pipe size, and normally it's the limit for carbon steel is 3 meters per second. So 3 meters per second. This is your limit for the carbon steel, so it doesn't get eroded. However, some point in so they determine, okay, I need a 2-inch or 1.5-inch line based on the amount of flow and the the amount of flow, and you can determine the diameter. Then along the line comes somebody who says, well, we can save money. Everybody's using the copper. Copper is a bit cheaper. So yes, you can use copper, and it can last as long. But if you still put it at 1.5 inch, what happens is your velocity is more suitable for your steel. But for copper, it's actually a lot. It's 1/3, like almost 1/3 softer. So, or 1/3 the softness of that of steel. So what happens is it gets eroded. So you could use this pipe actually, but if it's larger, if it's 2 inches or 2.5 inches, but that starts to go. It's a totally different ball game because then if you're using 2-inch or 2.5-inch copper pipes, then the cost might be like might become an issue. You say, fine, we're going to stick to carbon steel. And carbon steel has the issue because with the use of carbon steel in the HVAC systems, you do collect a lot of the corrosion products. So it's you have to really control that, and you have to. So in order to avoid this, people say, fine, we're going to use copper. But then you use copper, and without proper considerations, that's what's happening. So people come and say, okay, now we're going to use stainless steel. And you say, no, because this is surface water, so your chloride content is going to be there. It's impossible. There is going to be chloride content. Yes?
What was what was this copper tube used for? Was it refrigerant on one side and then cooling water on
This
the
water,
other?
yeah, this water. This is going for the coil.
Okay, so
Yeah.
refrigerant on one side and cooling water.
I think air at one
Just air?
side. I don't know the system exactly, but I know there was the water.
Cool? Okay.
And it's going, yeah, I don't, so I'm not looking at the system exactly. I don't have it. We can dig it for you if you want. But that's, I don't know if it's a refrigerant on the other side. I think the refrigerant cycle is probably carbon steel or something like, it's, yeah. But this one is just the water from one side, and I think the air at the other side is the coil.
All right. Okay.
Yeah,
So the corrosion's on the water side.
The water side. So the water.
Okay,
So this is
water
the side. That's the
Water.
inside diameter.
Okay.
So that's the inside diameter here, and it is actually. And this is the pipe. This is the remainder. It's kind of like curving like this. I don't know if I have another picture, but nope. So yeah. So that's the pipe here. And this is the cross section, and this is a zoom on the horseshoe pitting. And so this erosion is really happening because the velocity is just so high. The velocity is such that it's actually causing the copper to erode. You're just eroding it. So, and of course there is the corrosion type because you do have the pitting. So, and the flow accelerated corrosion, we have not a similar mechanism, we have different mechanisms happening in the feeders. So the feeders, the outlet feeders, the first elbow actually is also being noted. I think in the 90s they started noticing what's going on. We're having a lot of thinning in this area there, and it turns out as the PhD is departing, leaving the fuel channels, the outlet, it's very hungry because it's actually raised the temperature, and it's all zirconium, so it's not really picking up from the zirconium environment. So it is very hungry. It has the affinity. It has spot. You've actually increased the size of its appetite. So once it hits the carbon steel, with also the flow. So once it hits the carbon steel is very friendly, and it wants to dissolve, and it's softer, and it is, so that's what's happening. So, but after the first two elbows, we don't observe FEC in the PhD system. So primarily it is in this area, because right after you exit from the fuel channel.
So Claire was in the MCED department and was doing all this feeder thinning project basically. And in fact, in chemistry, we have changed many times pH to minimize dissolution of the magnetite coating.
Yes.
Because many times if your layer is getting dissolved at high temperature and different pH, you will get, along with the flow velocity, you will get some portion getting dissolved.
Yes.
So thinning will happen, right?
Yes.
So we have changed our pH values time to time, as I mentioned earlier, that
Yes.
in the unit 4 and 1 we have changed pH to minimize feeder pipes thinning, as well as to protect fuel bundles from getting the black coating.
Yes. So it's actually a very dynamic process, and there are right answers, but I mean, as time goes on, you keep changing and adjusting. You adjust something, realize something else needs adjustment, so you go on, and that's how it goes. It's a best effort scenario. You're trying to do that. So yeah, so it's pretty interesting actually. It all ties together. So and cavitation, corrosion, cavitation. So I had some slides for the cavitation. I removed it, but I think there's something here. So here, the velocity relay. So again, something like this. Again, I think this is a copper tube or a copper pipe, and you can see here it's really thin, and it's. So yeah, it is. I can see all the pitting. I think, wow, this is very pitted. You can see here. You can see the blue background is really showing everywhere. It's leaking everywhere. So yeah, that's from the increased velocity. But you can control it by design, the proper sizing of your, pipes. In this case here, so characterized by grooves, gullies, waves, rounded holes. Yes, you've seen all that, and exhibits a directional pattern. So you can see the claw, the horseshoe type. There's several of them, all pointing to the same. So these are the the hallmarks of the velocity-related erosion type of electrochemical dissolution of metal. That's what Anil was talking about. So it's not necessarily always just the erosion. You can also have the electrochemical dissolution. So you can control that. You can try to influence that by changing your pH a little bit. So you're increasing the pH.
Mm-hmm.
That's
No,
making it more alkaline.
adjusting according to the temperature and flow actually.
Very good. So again here, and that's what Anil was talking about, the removal of the protective magnetite film. This is in for the feeder pipes. And FEC has resulted in feeder replacement. I remember a few years, maybe 15 years ago, we also had, I was working on, well, more than 15 years ago, but 15 years ago that feeder was changed, maybe 12 years ago. It's in Bruce Power. I remember because I did the stress analysis for it, and we had something like 100 thous left, or 99 thous left. And then later on, they replaced it a few years later. So that feeders have been replaced. It's a very costly process. It's not very easy. You go there and say, okay, guys, let's replace the feeder. No, it's very detrimental. So I mean, detrimental to the outage. A lot of preparation and planning has to go there, and it costs a lot of money. So
Yeah, Unit 2 Darlington refurbishment, we have done.
we've done everything, absolutely.
Absolutely.
Yeah, the 480 feeders at each site, so it's 960 at both, because we know that those feeders. We've also done something, Anil, with this one. I think they changed the material. It includes a little bit of chromium.
That's right.
They increased this in feeders. It's carbon steel A106 grade B, which is the lowest, not lowest really, but it's the lowest grade of carbon steels. Nothing special about it. Nothing special about it. It's just regular plain carbon steel. However, and it worked fine. I mean, the fact that we were doing all this engineering and and trying to understand what's going on was actually a good decision 40, 50 years ago, because it worked fine. It's working fine. But now we are carrying more appetite for mitigating these effects. It's just an appetite. And the newer feeders in Darlington, actually, I think they've increased the chromium content. I think they have 2.5 or something. 0.3%. Very good. Yeah. So there you go. So the chromium actually will stabilize this passive layer. It has this effect. It's not stainless, but it has just a hint of So this is one thing.
So that will be a hot conditioning for making the protective passivated
Yes.
layer. So that's coming up with the hydrazine addition, those things for the unit 2 before startup.
Yeah, the chemistry is actually the chemistry folks, you guys are here, so it's very involved. It's a very involved process, and sometimes you're doing things for years, and then it comes and say, well, okay, now we have to condition for something. Now we have to accommodate the new design. So this is why it's very dynamic. Actually, it's pretty dynamic. Part of it is routine, everyday work, but the general, focus is like you can actually be doing a lot of dynamic and changing, the chemistry to accommodate, either design or change in design or change in our appetite to accept certain risks, things like that. So this is, so, so again, prevention, we talk about material selection, design considerations, controlling dissolved oxygen considerations, coato liner of the material for the feeders, we haven't done that. So for example, cathodic protection, we haven't done that. Moisture trap, so this is not feeders. But I mean, so for feeders, really we're doing the first 3 ones, and possibly more that's not mentioned here. But in general, for FEC, that's what we do here. And design considerations, we looked at the copper pipes, and so that's, Okay, so this one was, I was I'm sure everybody got touched by this. I was at another company which just spun off OPG, and that was in 2004. And Bruce Bauer decided, based on this, the Nihama incident, said, no, we want to do a more detailed FEC program. And so I got involved in this. And look at it here. The picture is not the best, but really, I think from what I remember, this is like a 20 or something inch pipe, and this is like 16 millimeters or 20 millimeters, something like this, 16 millimeters, the original. And since the 70s or the 80s, there was an PM to actually inspect. And the Japanese, that company did not inspect that one for years and years and years until it came, I think when it failed, it was, I think, 1.5 millimeters. And of course, all this is like you can open, and if you Google it, you'll get the report. So it's lost a lot. It's lost technically all its, and people were standing there, so workers were standing there. And when this blew up, or this kind of like, just ruptured, and you can see it's actually, this is the pipe, it opened up. You can see here, it's this is not the best of pictures. I've seen some pictures. It's actually all wrapped. It kind of like just unfolded, like a piece of paper like this, and just unfolded like that, like a rug, or like, and of course with all the steam blowing out, and people were around, and they died. I think a few workers, or a number of workers, actually were fatally injured, and others were injured badly because this is steam. It's condensed, but it's condensed water. But as it as it goes into the air, because the pressure of the atmospheric pressure is a lot less, so with the temperature, it flashes into steam. So very, very bad. So yeah, and it blew this 2 inches. So from there we started, I think everyone, OPG and Bruce Power, we had all these programs, but sometimes they were a little bit on the shelf. But because of this, it was like, no, we want to bring it to the front, front of the line, and actually go and do all the inspections and do calculations. So I was involved for a little while in Bruce Power to do calcs, to actually assume, and the FEC expert would say, assume this part really fails, or this part becomes effective. What is the minimum thickness that we need? So when they go and measure and they find they're approaching this minimum thickness, they can make an operational or maintenance decision to change. Things like that. So that was, in a sense, pretty useful for the industry, just a wake-up call. But these are the effects of so pipe, from 10 to 1.5, something like this. So I remember the 1.5, the 10, so it was pretty, that's a lot. This is like what, 90%, or 80%. So wall had not been measured since the beginning of 28 years. They keep just the PM, they keep deferring. So that's not good. Deferrals and of course localized corrosion combined with mechanical damage. So there's a load, because that part is like it has the load, is the stress on it, and occurs in turbulent or rapidly moving liquids. So the turbulent or rapidly moving liquids, of course, this is always happening because all our flows are very turbulent. They're not laminar flows. They're really very turbulent. And associated with sudden variations in pressure and turbine blades, propellers, and that stuff. So, the cavitation part as well. Actually, I had some pictures. That's a very good picture. If you look at it here, you're losing your, this loss of surface roughness actually is not good. It adds a lot more resistance on, so it actually reduces your efficiency, the efficiency of this blade here. As you can see, because of the formation, the very localized gas pressure for the liquid here is reached because the pressure decreases a lot, and that's